So I will really like to thank the organizers for inviting me to this short-term course on complex fluids. So today I'll be talking on a numerical investigation of complex fluid self-organization. So if we look into nature, there are several instances. I mean, there's no dearth of motivation if we look into nature as such. So there are several instances where the surface looks very smooth, but if you really look at it closely through under a microscope, it will appear that there are several irregularities on the surface. For example, if you take a lotus leaf, it will have these microscopic bumps. And what it does is that if there is a drop of water on it, it will not allow it to adhere to the surface, and it will help in self cleaning. Similarly, if you look into the gecko's feet, it actually has a network of hair-like structures, and what it does is it helps the gecko to actually climb the wall, so that the van der Waals interaction between the gecko's feet and the wall, it actually increases many folds. Similarly, we have all seen at some time these peacock's feathers. The colors really attract us very much, but many of us think that it is made up of pigments, but if you look at it very closely, again, it has arrays of barbules of different structures. So if light falls on it and gets reflected, they reflect at different angles, they interfere, and this actually gives rise to the structural colors. Similarly, if you look into a moth's eyes, it is made up of these beautiful structures that are very ordered, and this actually leads to a gradation of refractive index, and this gives rise to an anti-reflective coating where the wavelengths actually subtract with each other and does not emit any light. So what all these examples actually tell us is that if the surface is patterned, is physically patterned, that also gives rise to several important features like hydrophobicity, like adhesiveness, like structural color formation or optical properties. So the question that actually arises is how to engineer such small length scale structures artificially, right? Whether it is possible to do so at all or not. So that is the question that actually should be asked. So yes, it can be done, and there are different approaches to do it. So one of the approach is a top-down approach, right, which is basically known as lithography. So it's a micro machining or cutting out of materials to create these patterns. So these are known as hard lithography, which are done on silicon substrates. The other method is mainly of chemical vapor deposition, or is basically a bottom-up approach where the molecules are clicked together to form a super molecule of definite requirement. So both these techniques, which are very much in use, they fail when you actually try to do patterning on soft surfaces. Why? Because this hard lithography, it works on hard surfaces, right? So it totally fails on polymeric surfaces, and this self-assembly route is a very time-consuming route. So in this talk, I will be basically focusing on the self-organization in polymeric thin films, right? How this can give rise to different types of patterns that can be used. Now, if we see why should be done, we have seen into nature, and actually this can be put into applications, right, where it can be used as smart adhesives, as hydrophobic coatings, right, which is very much in need when we are doing microelectronics and things like that. And this can be used as anti-fouling coatings, anti-reflective coatings, anti-corrosive coatings, right? Any type of coatings that we want, these patterns can be made into use. They can be used in MEMS, in microfluidic devices, where you are trying to develop and culture some cells. So there are different types of optoelectronic devices where this can be used. So the application range is huge and enormous, and the list is really endless. So before I go to my topic, I will like to revisit some of the instabilities that are present in nature that we may be seeing in normal day life, everyday life. For example, we often come across this Rayleigh plateau type instability, right? Where we see that if there is a thin film that is of water that is falling down, it often transforms into smaller droplets rather than a thin film. So this type of instability occurs because of the surface tension and because of the Laplace pressure and surface tension effects that is present over there. Similarly, if we boil some liquid, you can see that there are certain structures appearing because of instabilities on the surface. These are known as Rayleigh-Bénard convection instabilities. This happens when a hot fluid, because of gravity, tries to come up, right? And when you are hitting it from the bottom, because of the density becomes lighter, and because of viscous rack effect, right, this gives rise to different polygonal structures like this, right? So this is an instability because of the viscosity and the gravity effects for that example. Similarly, we know about this manganese fluids, right? So if there's an ink that you let to a drop of ink in water, so there is some alcohol over here also which helps in evaporation. So what is happening that the ink drop is at a surface tension that is very lower than the water. So it tries to spread. So the flow is from the region of lower surface tension to higher surface tension, and this actually gives rise to wonderful patterning, finger-like patterning that is happening over here. Similarly, we may have seen while we are mixing some cream on coffee that because the cream is a denser liquid than the coffee. If you see over here, because of gravity, it is trying to come downward, and there is always a surface tension that is trying to oppose it. So in all these examples, we see basically there are opposing forces that are acting, and that actually gives rise to different instabilities in the system. So the instabilities or the self-organization that we will be talking today on will be on soft thin films. So these soft thin films can be actually categorized into two different genres. One is that of liquid thin film, and the other is that of an elastic thin film. So they are different, I will tell in different ways. Like in a liquid polymeric thin film, when it is cast over a substrate and the thickness of the film is less than 100 nanometer, there are excess intermolecular interactions that appear between this surface of the film and the surface of the film and the substrate. And this excess intermolecular interaction is higher near the region where the thickness is low, and lower in the region where the thickness is higher. So this actually gives rise to, when there are certain fluctuations, this gives rise to flow from a region of higher pressure, that is lower thickness, to a region of lower pressure or higher thickness, and this gives rise to this type of dewetting patterns, as you can see in the figures below, that there are dewetting patterns. Even if you spill some water on your tabletop, you will see that if the layer is very thin, it actually gives rise to dewetting. Um, Similarly, if there is an elastic film, so these are all experimental results that can be seen. These are done by Reuters group in the year 1992, and they have seen that in wetting thin liquid films, the long wave, the instabilities that appear, or the wavelengths at which these patterns appear, are long waved, and it actually varies as h square. Whereas in an elastic film, which is a soft film, when it is casted again on a substrate, and there is no restriction on the thickness, it can be of micron size. But when a contactor is made to approach this film, then there is interaction from the top of the contactor that tries to deform the film, and there is the intrinsic elasticity film that tries to restore it. As I've told, all the instabilities happen because of competition between two antagonistic forces. So in this case, the antagonistic forces are the intermolecular interaction between the film surface and the contactor that tries to destabilize the film, and the restoring force, which is the elastic force that tries to level out these instabilities. So when the force is critical, that is when the contactor is at a very small distance, what happens is that the planar surface of the film actually gives rise to this ripple like structures. These black regions are the regions in contact with the contactor. So but this and when this contactor is retraced back, it is seen that these instabilities pursue for certain distances, and definitely again everything becomes laminar when the snap of distance where these instabilities again go out is at a much higher distance than the critical distance where the instabilities were first seen during the approach mode. So there is a hysteresis present in this type of instabilities in elastic films, and what is difference between these two type of instabilities is that one, these instabilities are much short wave. For example, the wavelength, the distance between two patterns is actually 3h, which varies as the thickness of the film. So it is short wave, which is very much different from the liquid films, which are long waved, right? And moreover, in this liquid weighting films, the instability is very much dependent on the nature of the substrate, right? If you change the substrate, if you coat the substrate, then the wavelengths would be different. But in case of elastic films, when we coat the contactor or bring in different types of contactor, whether it be a glass contactor, whether it will be a silicon contactor, the wavelength always remained as 3h. So these are the two different types of instabilities we will have seen in thin films in different configurations. So we will like to uncover why this type of instabilities are happening, basically through numerical modeling. So we have told about the advantages. There are definitely different disadvantages. For example, our cornea have a thin layer of liquid film on top of it, and if it is made unstable, then it may give rise to dry eyes. Similarly, in industrial boilers, when because of heating a certain layer, the thickness becomes very less, then there can appear to be hot spots. And of course, dewetting, nobody wants the dewetting of carbons to happen. And integrated circuits also, these materials are joined by adhesion, and if it is becomes if there is some de-adhesion happening, right, this will give rise to a lot of disadvantages. So not only so we should look into solutions where we can maintain the homogeneity in such cases, and also we'll look into criteria where if they deviate in certain ways, then how to put them into advantageous applications so that the physical properties can be enhanced, right, in those scenarios. So basically, in our content, we will be today looking into soft adhesion. So we'll be looking into instabilities in elastic thin films. We'll be looking into miniaturization in liquid thin films. Try to understand that. And as we have said, that the liquid and the elastic thin films actually have patterns because of have different types of patterns. So we like to develop a unified theory of instabilities in these films, right? Why this is happening, we will try to find out through a unified theory, which will tell us that why this is happening. If we have time today, we will be looking into your self-organization in certain other complex fluids like wet granulars, right? If we have time, we will move into that also. So let us first do into hydrodynamics of thin liquid films. So as we have told that this is a thin liquid film which is cast on the substrate. So why we are telling self-organization? Because this is a technique by which the film rearranges amongst itself because of some force field, right? Whether it is an internal force field or whether it is an external force field. In this case, if it is cast on like a thin film, like a coating, like a paint, right? This is exactly what happens, right? There is a substrate on where you apply a coating of the film. So there is a bounding fluid on top of this liquid film, and there is an interface that is created. So in this, so this is the interface that has been magnified over here and shown. So in this film, if this thickness is less than 100 nanometer, so this may be the initial thickness of the film, or it can happen that because of certain disturbances, the initial thickness of the local thickness actually gets down to this thickness. And when it is less than 100 nanometer, there are excess intermolecular interactions that come into play, because of which this film tries to be attracted towards the substrate. So the flow field in this fluid can be defined again. If you take a shell and do a balance of force field, this will be the force balance that will happen. This is the simple Navier-Stokes equation in x and z component. So the geometry, if I look into it, x is the component in the lateral direction, z is along the thickness of the film. So the height of the film is along this z direction. So we write the x component of Navier-Stokes equation and the z component of Navier-Stokes equation, and then we write the mass continuity equation. So this is simple for any type of liquid flow that we are looking into. So the first thing that we do is we go into the Navier-Stokes equation to look for a solution. The only thing over here is that instead of body force, which is of gravity, we are neglecting it because of the dimensions of the films. As I have said that the thickness of the film is in the range of 100 nanometer. So in this range, the gravity force can be neglected compared to the other forces. So U and W are the velocity components in x and z direction. P is the pressure inside the film, and what is there instead of gravity is the excess pressure inside the film due to the size of the film, as I have said, because of intermolecular interactions. So this is the excess free energy per unit area of the film. So this is denoted by phi, or the body force, right? So this is acting because of the interaction energy that is present because of the small thickness of the film. Now, if I look into the boundary conditions, if this is the boundary of the film at the top, so this is the normal that is happening, and and capital T is the tension at the top, or the traction at the top surface. So basically, at the top surface, the balance of the traction and the surface tension can be given by an expression like this, where T is traction on the top surface and T hat is the traction on the underlying surface. And basically the normal is given by a condition like this, and the tangential velocity or the tangential unit vector can be given depending on the surface profile, right? They can be given by N and T vectors, something like this. So if I look at the, so if we want to solve the Navier-Stokes equation, we have to write the boundary conditions, understand the boundary conditions. So if you look at the shear stress boundary condition at the top surface, it is given by, so what we have done is basically the stress balance equation. We have done a dot product of that with the tangential direction, and if I simplify by putting in this these stresses T that is appearing and the surface tension, this is and there you can see that in this type of a film we are not constrained. We are constrained that the surface tension is constant throughout the lateral direction. So basically the gradient of surface tension along the tangential direction is going to be, there is no gradient, right? So it's a constant surface tension term. So your right hand side of this equation will be 0, and the left hand side, when it is equated, it can be recast in a form which depends on the surface profile, right? H, for example, is the thickness of the film, and all the subscripts here actually denote derivative with respect to either x or z direction, with the different directions. Similarly, if I do a normal stress boundary condition where we take the stress balance equation and then do a dot product with the normal direction, we get a pressure jump along this direction, and that can be equated to the, again, the surface tension term over here. And then we can apply the kinetic boundary conditions as z is equal to hxt, which appears looks something like this. So, and at the base, this all was happening at the top surface, and at the base of the film, we have there is no slip boundary condition, which is given by u is equal to 0, and of course we are not considering a porous substrate. So in that case, your z component of the velocity vector is also 0. So w is also 0. So these are the boundary conditions that are required to solve my thin liquid film equations. So I have told you that instead of gravity in these films, because it is of less consequence because of the thickness of the film, we will be considering excess intermolecular interactions. Now you may, and this mainly happens because of a dipole-dipole interaction between two molecules. You may have read about it, but then and you can see over here, it is written over here like the interaction energy phi is alpha by r to the power 12 minus beta by r to the power 6, where the negative term over here is because of the attraction, while the positive term is because of the repulsion between these two molecules. If you see over here, this is between two molecules, and this actually this force actually dies down over certain radius of angstrom distance, right? So this force field actually decreases very fast, right? So how do you think that even if the film is of 100 nanometer, we are saying that if it is less than 100 nanometer, then excess intermolecular interactions is coming into play. But here, if you see between the molecules, this force actually dies down very easily. So how is it valid across 100 nanometer? So for that, what we need to do is understand that this interaction is between two curved surfaces, or is between two, even for two flat slabs if we consider. So these are not between two molecules, but it is integrated between the two slabs where all the molecules are present. So basically, if I look over here, so when we look into the van der Waals interaction between two molecules, it dies down faster. But if it is between two surfaces, it actually persists over a distance that is about 100 nanometer. How we can find out what is the expression? Does the same expression remain or not? We can find this out. So if there is a molecule of nature 2 that is remaining at this z is equal to 0, right, and this is a slab of 1. So and if I take a ring-like structure over here that is given by this shaded area, and we find the interaction between this molecule and the molecule present over here. So we can see that in this shaded area, what is the number of molecules that are present. So you can find out that ρ1 Na by m1 is m1 is the molecular weight of this material. So you can find out the total number of molecules that are present per unit volume. So the first bracket on the right hand side is expression that only, where dV is the volume of the shaded area, and this is the interaction potential that we have over here. So this is the potential that this molecule that is at a distance of r from this ended molecules over here denoted by the shaded region, it will experience a force something like this. So you can integrate it over between all the molecules in the slab, selected molecule 2 and the entire slab 1. So for this, you have to go for the k distance from 0 to D1. So this thickness of the red material over here of slab 1 is D1, and you can go from 0 to infinity, because we are considering that that the slab is extending towards infinity in the x direction. So what happens is that if you integrate it over here, you will get that this is what is happening between a molecule and the entire slab. This is the potential, or the interaction potential, that is valid. Similarly, so this is between one molecule and the slab, but we want to know what is the interaction between the two slabs, especially between, if the slabs are at a gap distance of d, and the thickness of the slabs are d1 and d2. So mostly the gap distance that you are seeing over here, as I've told, is in the nanometer region, whereas the slabs can be, slabs are are the materials, for example, like the coating. So these thicknesses can be of the will be much thicker. So the substrate or something. So this D1 and D2 can be considered to be infinite compared to this D distance. So once one of the molecule of slab 2, you have found out the interaction compared to slab 1, you can integrate this potential throughout the other slab, right? So if you do so, the interaction potential between slab 1 and slab 2, so phi double prime was the interaction between one molecule and the entire slab 1. So there are so many molecules, rho 2 n2 m2 into dz is the volume of the molecule that is present in slab 2, and if we integrate it, we will get the entire interaction between these two slabs. So this is the final expression that we'll get of the van der Waals interaction, and the energy between these two slabs. And what we can do is we can make D1 and D2, because these are much higher compared to the separation distance. We can make this go to infinity. So this is the ultimately the energy that is present between these two slabs, which is very much the distance, the effective distance where it is effective is much higher than the angstrom level. So it is present in normal fluids up to 100 nanometer. So this was a potential interaction, excess interaction potential that was present because of the thickness of the film, as I've told. And if it is less than 100 nanometer, you can see that if the distance, so if you can see say this interaction energy, or the interaction the force can be the derivative of this interaction energy, that is inversely proportional to the to this gap distance. So if it is very much higher, so if the d is very high, then the interaction potential, of course, will be very less, and if it is greater than 100 nanometer, it will go to 0. So there is no force present if the thickness of the film is greater than 100 nanometer. So to solve this, one needs to non-dimensionalize the problem. We do this scaling. So in this problem, we take the thickness scaling, and we try to do all the scalings with respect to that. And for time, it is a kinematic viscosity by the square of the thickness. So once we do that, we can rescale the entire Navier-Stokes equations and the boundary conditions properly. Right, so we have done just the scaling, and we have written in terms of the non-dimensional things. Next, what we do is what helps us to solve this problem, right? Otherwise, it could have been solved in CFD. The whole of Navier-Stokes equation we don't want to solve. We just want to simulate the thickness of the film and try to see how it is behaving. For that, what we do is we take a lubrication approximation. Now, what is a lubrication approximation? Is that because in these films, the viscous stresses are very high, and the inertial forces are considered to be negligible. So the evolution of the film occurs at a very slow time. So the spatial and the temporal variation of the thickness is very slow. And what has been found is that the wavelength in the experiments, as I've told for liquid films, that the wavelength is very long wave. So what we do is we try to scale this, again the scaled equations, we do a rescaling with respect to k, which is a wave number, as you can see, and it is related to the wavelength of the film which is considered to be very high compared to the thickness, because lambda is very, very higher than the thickness. This actually gives rise to k, rescale variable, right, which is actually very less. So if I scale all these lateral scales and other scales which are with this k variable, so we can get an order of 1, because this k is very less and x is very high. So if I multiply them, then all the important variables, right, and its derivatives are considered to be of order 1. And so we can expand the dependent variables like the velocity and the pressure fields with respect to this k variable. So once we do it, we recast the non-dimensional equations into this form. What we do is we take the lowest power of k and equate it, and then your x and basically your x and z momentum equation converts, and your kinetic energy. So all the top equations gets converted if we take the lowest powers of k, and similarly then and if we can consider that k actually tends to 0. So these are the equations that we mainly get for the no slip boundary condition, for the kinetic boundary condition, and the shear boundary condition. So and the normal boundary condition over here. So these are the conditions that we boundary conditions, and the main equations can be recast if we take a lubrication approximation like this. And the the governing equations in the dimensional forms are simply given by this. All the boundary conditions you can recast again into the dimensional form. So the main thing of solving a thin liquid film equation is to what we are doing is that definitely different from maybe a fluid in a pipe flow and other things, is that first that the body force is important, which is different, and also we are considering along with approximation that we don't do for normal fluid flows, right? Because here the wavelength is because the viscosity of the flow is considered to be viscous terms are quite higher compared to the inertial terms. So once we do this, we can get the profile. For example, we can integrate the x momentum equation twice. You get two coefficients. You can get help of these boundary conditions. Basically, these boundary conditions are the no slip boundary condition at z is equal to 0 and the shear stress boundary condition. And from that, you can get this is the velocity profile of the fluid in the u direction. Similarly, using the incompressibility condition and the impermeability condition, one can get what is the velocity component in the z direction. And similarly, putting it into the kinematic boundary condition and using the pressure jump at the interface, the normal boundary condition, we finally arrive at the thin film equation we want to solve, right? You can see that this expression, that this some of the things that you see is that this is for an incompressible thin film, yes, and this is a highly nonlinear equation, is a partially differential equation of fourth order, right? So it is very difficult to solve analytically to find out the thickness, as because this thickness is, as you were saying, is it varying? It is varying across x and also evolving with time, right? So how the thickness of the film? So this thickness will give you how the liquid film is behaving, right, as we yes, as it is evolving, right? Because when the intermolecular interactions are coming into play, how this liquid is coming and making a contact line with the substrate, and how it is deviating, right? So this is the equation that we solve in thin liquid films. So before telling you how it is solved and what is the actual profile, scientists mainly do what is known as a linear stability analysis. So what is done in linear stability analysis is that this is definitely not an entire analysis, but it gives you a glimpse of how the thickness is evolving in space and time, right? Linear stability analysis gives a lot into understanding the instability in the system. Of course, it definitely does not give you the real life scenario because it's a linear analysis, and you have seen that the actual equations are totally non-linear. We will also see certain cases where the linear stability analysis does not give you any result, right? What the actual real situation is, but it helps to understand the system. So what is done is that you have understood that the thickness initially was uniform, so it was H0 throughout the film, and we may perturb the surface with perturbation with an amplitude epsilon, which is very less than the thickness of the film. So basically you can consider that epsilon fxt, this term is very less than H0, and in linear stability analysis we will show later that this is considered to be also a sinusoidal type of perturbation. So how f varies with x and t, we will see a little later. So what we do is we recast this equation, the actual thin film equation, around this H0, right? And we write it in terms of epsilon and f, right? And then we can consider that this function f is sinusoidal, as I have told, and it is evolving with time. So it has a time component and a sinusoidal component, and you can consider that this is a trial function that we want to fit in and try to see how it evolves with time. So this is a fluctuation on top of this uniform thickness that we want to see, and we want to see that whether this perturbations, so we perturb the initial surface with this type of disturbances, and we want to see whether this perturbation grows or not, right? So when we put this function in this equation and we get rid of the higher order terms of epsilon, because epsilon is itself a very small quantity. This is the dispersion relation that we get, or this is also known as a characteristic equation or a compatibility condition. This is an equation with respect to the growth rate of this perturbation, where k is the wave number of the wavelength as it evolves. So what we want to see is, what this linear stability analysis tells is that if this k is again the wave number of the instability, and if we see that the perturbation leads to the value of omega to be greater than 0, then these perturbations grow in terms. It causes this instability. When it is less than 0, if you perturb it, after some time it will die down. And if it is w is equal to 0, it is critical boundary condition between stability and instability. So if we are looking, if we are getting a dispersion relation with the growth rate omega to be less than 0, so then all the instabilities will die down, which will be a situation which will be a situation in case where like in a homogeneous paint, if you want to create, right, or in case of the corneal film that you want to do, right, you will look into condition that into conditions of H0, gamma, H0 that will lead to omega less than 0. Otherwise, if omega is greater than 0, then this will lead to instabilities and the growth of these instabilities with time. So this is the dispersion. Now let us see that in case of thin liquid films, what leads to a growth rate that will be greater than 0 or less than 0. So the first term on the right hand side, if I see, H0 is a constant factor that depends on the thickness of your film. Surface tension is, of course, if surface tension is positive, that is mostly in cases, right? And k to the power 4 is a fourth power, so it is always a positive quantity. So the first quantity on the right hand side is negative. That means that omega, the contribution of this term is actually leading to a decrease of omega or a negative value of omega, right? So this is actually the surface tension term. So the surface tension term always will not like an instability to happen. It will try to make any instability die down. So this equation is a reflection of that only, that the surface tension will try to oppose any type of instability that is created in this film. What is the right hand side doing? So the right hand side is dependent, if I see, on the interaction potential, right? So on the type of interaction that is present. We have talked about one type of interaction, like the Van der Waals interaction. There can be a lot of interaction, as I have told. It depends on the substrate. It can be it can have a different chemical nature, and for that, it can be an electrostatic interaction between these films. It can be an acid-base type of interaction. So it's not only Van van der Waals interaction, I've told only one which is present, even if there are no other interactions present. So this is always present anyway, right? But there can be other types of interactions that can be present also. So if phi h naught this is less than 0, then we can see that this second term will have a positive effect on omega. So this phi, in case of van der Waals interaction, evaluated, this h naught means evaluated as at h naught. So you can see that this is a by 6 pi h cube. So this quantity needs to be negative, right, to have this effect. So phi is this a by 6 pi h cube, and pi h naught is a derivative with respect to h. So that will make this quantity negative itself. So this will become positive. For this, what we need is the Hemaker constant to be positive, right? So in those films where the Hemaker constant A is positive, this will lead to instability in the system, right? And when this term, so this term will be positive, and this will lead to the growth of the waves that we have seen. So if I draw this omega as a function of k, you will see that there is a region between 0 and kc. So this is a critical wavelength below which there is a region where the growth rate is positive, beyond which if you increase k means that the wavelengths are very, very small, then you don't get any instability in the system. So if the wavelengths are, again, this is a proof that in case of thin liquid films, the wavelengths are actually very long wave. So if it is k is just the inverse of the wavelength, so as we have defined earlier also. So if the k is between 0 and some critical values, you can see that all the wave modes are positive, right? Amongst this, there is a wave mode called the dominant wave mode, where the waves that you can create because of the instabilities are growing at a very fast, at the fastest rate, and the number of droplets arising due to instability is actually inversely proportional to lambda m square, and k is the inverse of lambda m, right? So if you see that if A is greater than 0, the fluid partially weights the surface, which means that the fluid layer breaks up into droplets if the Hemaker constant is greater than 0. If it happens that A is less than 0 between two surfaces, that means that the fluid surface is repulsive to the substrate. It does not want to weigh, so it is repulsive. It does not go to come down and deweight the surface. So in that case, we don't get any instability. So the spreading coefficient and the Hemaker coefficient are again negatively related. So one can see that if A is greater than 0, that means that the spreading coefficient is negative in that case, right? So that actually leads up to this beating up. So that is happening. So you can also get the time of rupture from this, right? So if you, so this is the perturbation that we are giving to the system, that H is A0 plus epsilon Fx, where Fx is a function of this. So at rupture, what is happening is that the thickness is actually touching the base. So H is actually 0, and sin kx can be considered to be -1 in that case. And from this, rough time of rupture can be obtained by tau. Of all the omegas that is there, the maximum omega will give you the minimum rupture time, right? So this is a linear stability analysis that gives into an insight of the instability. To understand the nonlinear equation, you can see that this is a partial differential equation, and it is highly nonlinear. So what we do is we can discretize it over a domain like this, like by finite difference method, where we can take for the distance for the distance derivatives, we can take your central scheme, and we can write these equations. You can see how we have done these discretizations. If you have an idea of finite difference scheme and how central scheme can be used, you can see how this different functions can be put in and can be actually found out, right? And we can actually solve these equations at all, and we can, for boundary conditions, we mainly do periodic boundary conditions, because as I have told that the length of the of the substrate can be infinite. So we don't do the entire domain, but we can do a small portion of the domain, and we can include periodic boundary conditions at the end. So you will see that you will get this thicknesses. You have to solve this for h at different I or the spatial location point, and at a different time you need to evolve it. So what happens for these films are that these are very stiff equations. Actually, if you want to solve this, what do you mean by stiff equation? Is that the nature of the solution, how the thickness is evolving, is it takes, as I've told, that it takes a lot of time for the whole evolution. That's why a long wave approximation has been taken, and the nature of the evolution is different at different time scales. So this though it looks like an answer equation that has to be solved at n number of discretized space points. These are coupled equations, but it cannot be solved so easily by any RK methods, for example, because these equations are very stiff. Because this thickness evolution is very much dependent on the thicknesses that on the time scale. It is the nature of the thickness is different. So for that reason, we actually solve this by Gears algorithm, and Gears algorithm is a package that you can get in NAG library, and this is a particular subroutine which is used to solve very stiff equations. So these equations cannot normally be solved by any type of RK methods. So this is done by Gears algorithm in NAG's library. So we will show you that in case of a half lambda, how this film is evolving. So this is the surface which has been perturbed, and this wave is actually getting modified. Here you see that the droplet has that the initial thickness has reached the surface at near zero, and the liquid film is forming a rim, right? And this rim is getting filled up by liquids, right? And this is ultimately forming a droplet, a half droplet, right, in a length scale of half lambda. So this is the half lambda where this type of a droplet is formed, right? This lambda is the lambda that is actually given by the LSA, and this is a nonlinear simulation showing how these instabilities look like. So this is this is, you see the grayscale image. This again is the instability at the initial time step, which evolves with time and give you different dewetted structures, as you can see over a length scale of 2 LSA. So this, like for example, you can ask me what help does it do, right? By this dewetting, as I've showed that these patterns can be made into different use by using them. So as patterns substrate where the physical nature of the surface can change. These can be used as for thin film force microscopy, because it's very difficult to understand what type of force field is present in a fluid film, right? There are very not very many measures, right? Yeah. So this is a definite measure of the type of interaction that is present between the liquid film, depending on the number of droplets and the wavelength that is found. If it is found to be varying as h square, you know that van der Waals interactions is present. If it is varying differently, you know that different interactions may be present, and you can find out that what are the interactions that are present inside the film by looking into the dewetting pattern. So we have seen now that the patterns can be used for different purposes. One of the purpose is that how to miniaturize these patterns, right? How to get these patterns and because we know that in thin liquid films we are getting long wave patterns, so it would be always better to have patterns at a very small length scale, because then what happens is the physical properties can be enhanced very much if these patterns are at a very small length scale. So what we have looked into is that if we have always considered that that all the physical properties of the film is constant. As one of them, we have considered the surface tension is constant. all these properties that we have constant, the surface tension, the viscosity, the density, if they are not constant, if they are varying along x, or if they are moreover varying over thickness, if they are varying over time, this will all have an effect on the evolution of the thin film. For example, in
It's
this
12
case,
hours.
what we have considered is that the mobility here is a function of thickness. So the mobility factor is actually given by h cube by 3 mu h. In this particular problem, what we have considered is that the viscosity is if the viscosity is varying with the thickness, uh, and in this particular problem we have considered that the viscosity is lower at lower thicknesses and higher at higher thicknesses. Why this happens? Because in certain entangled polymers, what is happened, there is an evaded volume, or there is a temperature at the substrate is very high, so the polymer layer cannot go over the melted region. So the viscosity near h is near the z is equal to 0 or 0 is actually near the interface of the substrate is actually very small. So in that case, your mu is varying with thickness like this, and the mobility in case of a constant mu is given by actually h cube, varying as h cube, as given by this blue curve over here where m is equal to 1. For cases where mu is varying like the way that we have said, we have seen that the mobility is not following a monotonic behavior. It is first increasing, reaching a maximum, and then dropping down and reaching the constant viscosity curve for higher thicknesses. So this for higher thicknesses, of course, as we are going higher up, we are constrained. So the viscosity as a function of h can be given by this behavior, where we can see that if the thickness is very higher, it is actually going back to the constant, to a bulk viscosity, which is not very much changing with the thickness. So it's basically going back to the constant thickness behavior. So from the linear stability analysis, as we have told before, that lambda m varies as the inverse of phi h0 square, and as phi h0 square is inversely proportional to the h to the fourth, so lambda m varies as h square in normal films. In this films also it does, because none of these quantities contain viscosity in it, right? So if the viscosity is varying also with thickness, lambda m does not have a signature for this. So here you see that the linear stability analysis fails to tell that whether there will be any change in lambda m, and it tells that it is the same as a constant viscosity case. There's no difference. But the time of rupture, on the other hand, has a variation of mu h naught, right? And it shows that the time of rupture will definitely be dependent on it, right? And we will see how it depends on it, and whether there is any change on the wavelength because of this mobility variation. If the wavelength is lesser, we should understand that it can be put into good use for helping in patterning with enhanced functional properties. In case of viscosity variation, you can see that it actually leads to very sharp holes and very flat profiles. That means by taking out fluid at a very small level also, it can create instabilities, and it can be seen that the time of rupture for these cases where there is a variation of viscosity is actually very small. So it actually ruptures at a very small time scale, as given by the linear stability analysis, which also shows that the time scale will be smaller, but it does not tell about any length scale. And this is a pre-rupture phase, where also it shows that the time of rupture is very less, and the difference between the normal case and this case is that it gives you flatter profiles at the pre-rupture stage. Now, in the whole growth phase, what we have seen that this is the first picture that is shown. What we have seen over here, that if for the from the fourth region, if we see that the pressure over the curved region will be higher because of Laplace pressure, so fluid will flow in and try to level out this because of the surface tension effects, and this gives rise to a half droplet. What happens so different in this case is that in these cases, fluid, instead of leveling out, what is happening at this thicknesses, when the thickness of this region near in front of the hole is actually very less, then it can be seen that the van der Waals interactions here is again very high in this case, because the mobility is very high in this region at the lower region, because the viscosity is very less over here. So this helps the film to come in contact with the surface once more, right? So you can see in a region of half lambda where we previously have seen a half hole, we are seeing a full hole in this case. So basically what we are doing, what we are seeing is that we are so these are the blue vertical lines over here are the regions of the primary holes that were growing in case of normal holes, and these red regions are the regions where the secondary or the satellite hole is growing. So you can see from this figure also that there is this development of satellite hole growth between two primary holes, which is happening because of this type of a mobility difference that is created because of this viscosity variance. And this viscosity variance is definitely a possibility, because not all, I mean, these films are to be casted in this form, you need to have a melted surface on which you have to have a surface on which you cast this melted surface. So in a second case where the viscosity is very less at the top and the viscosity is very high at the bottom, we have seen a different phenomena. So this is a different opposite thing than that was happening in the previous case. Here the mobility is low at where the thicknesses is very less, and where the thickness is very high, the mobility increases, which mobility increases. The viscosity is also behaving in a similar way, that the viscosity is very high at the bottom and is very low at the top. You can see that this actually gives rise to in normal cases this gives rise to instabilities and droplets only. In case of this type of films, you can see that there is a secondary range of thickness of droplets that is appearing. So these orange regions are the regions where the primary droplets are going, and this is a bimodal distribution of droplets, right, where the droplet in between has a different thickness than the droplet that is surrounding it, right? So this can be put into good use where we are using this type of patterns for optical properties, right? So there will be reflection from, as we have talked about this peacock's feather, which is happening because of reflection from different barbules of different sizes. So we can create these patterns of different sizes, right, from which the optical property of the surface can be made to be different, and different nature can be evolving. So these were about the thin liquid films, right? We have seen the Navier-Stokes equations. We have seen how it is formed, right? And we have solved it by finite difference method, by NAG library for solving stiff equations that we have seen. Now, in case of elastic films, things are a little different, as we have told, because because of the patterns that are forming are actually forming spontaneously. There is no time evolution. The moment you bring the contactor at a certain position, the elastic film will be spontaneously formed. And as I have told, that the wavelength will be proportional to 3a, so it is already a short wave instability. So if I look into the mathematical modeling, as before we have said that this is happening because of competition between two interactions. So this is a surface interaction potential that tries to destabilize the film, and the elastic energy that tries to restore the film. So you can find the surface displacement, you can write it in terms of the Fourier coefficients, right? And this surface interaction potential, as we have told before, is composed of van der Waals interaction and the bond repulsion. But here you have to see that in case of liquid films, this interaction was between the film surface and the substrate. In this case, it is between the surface of the film and the contactor. So this is the difference between these adhesive films and the wetting films that we had seen before. And of course, the elastic energy that is over there. So you solve these equations by solving the rigid boundary conditions at the substrate and the shear free boundary condition. At the interface, there's no shear, right? So that we have seen in the liquid films as well. So the boundary conditions remain almost the same. There are two types of energies over here, and what we do is The displacement fields that will solve the problem will solve the stress equilibrium condition, which is similar to the force equilibrium condition that we have seen in Navier-Stokes equations, the incompressibility condition, which is similar to the incompressibility condition in case of liquid films also. So what we do is, in this type of films, we do energy minimization. So for that, we construct the displacement and the pressure fields are to be of sinusoidal nature, as over here. You will see that there's no time over here that is written, because these are spontaneous evolutions. This does not take a time to evolve. These are very spontaneous films. So the U1 that you will see is only dependent on x1 and x2, the two directions only. And so when you cast these trial functions into the main stress equilibrium condition, incompressibility conditions, you will get that you get a biharmonic differential equation, which is fourth order. And this is a general form of the equations where A, B, C, D are the constants that you need to solve, and you can solve it by taking care of the boundary conditions that we have already taken. So, so here one can do is that one can trace the normal traction at the surface to get how the wavelength is varying by doing a linear stability analysis that will be doing so. But the total energy, if I write in terms of all the Fourier coefficients, like the surface is represented with respect to this Fourier coefficients. So if we can write this total energy, which is the sum of this elastic energy and the potential energy in terms of this Fourier coefficient, the task of the nonlinear analysis remains to find the Fourier coefficients for which this energy is minimum. So instead of going there to the nonlinear analysis as we have done for the liquid film, we can do a linear analysis. We have to, where we can take a single Fourier mode and try to see that if I minimize this energy, what are the conditions we get. So if I minimize this potential with respect this energy with respect to the single Fourier coefficient, we get a condition like this, where the right hand side, if you can see, it is a ratio between y, which is the interaction potential, and mu by h, which is the elastic stiffness of the film, right? And when we cast this film with this potential with respect to kh, you can see that there is a critical value of this interaction potential, above which there is instability present in the system, below which there is no instability, and there is a critical wave number where this instability start, right? And this lambda you can see as 2.96h. So this actually tells you very important things. One, that the wavelength is close to 3h, as we have seen in this experiment. So it is dependent on thickness. It is not dependent on h square as we have seen in liquid films. The other thing that is seen over here, that there is a critical interaction force. What does that mean? That if you are bringing the contactor from infinity, there is a critical distance at which these instabilities will first start, right? So if the gap distance between the contactor and the film surface is very high, then the interaction stiffness is very low, and then there will be no instability. So it will be in the stable zone, right? So the film surface will not be giving rise to any patterns. But if it is within this instability zone, when the interaction stiffness is higher than this critical value of 6.22, then we will see instability in the system. And what type of instability we will see depends on the optimized Fourier coefficients that we obtain if I try to minimize this energy. That can be done by a conjugate gradient method that we actually use to find out this optimized coefficients at any point of the contactor. So the first the contactor is brought at a contactor at a critical distance, we see the instability that is happening, and we then can retrace the contactor back and find out the distance up to which this instability is persists, because this is what was seen in the experiments, that the critical distance at which the instability is first started and the snap-off distance where the instability is persisted were actually quite different. So whether we can find out these hysteresis or not, that can be done by a nonlinear stability analysis. So even going further, before the linear stability analysis, what we can do is we can write down this energy with for a single Fourier coefficient with respect to the wave number, and this red region is the region below the critical distance. So when d is below the critical distance, when the contactor is approaching, we can see that there is a shallow minimum over here, which is the global minimum. So we can understand that why this critical wavelength at 2.12 we are getting over here. But when we are retracing back the contactor, what is happening is that this 2.12 is now becoming a local minima, whereas a flat film is a global minima. Because while bringing down the contactor, we saw that the flat film was indeed the configuration that we are seeing. But when we are retracing back the contactor, the energy of the film is already in this metastable minima, right? So in order to go from this metastable minimum to this flat film configuration, we need to cross an energy barrier. So that's what we see in these experiments, that when the elastic film is already cast, already in this pattern state, it cannot go back to the flat state just by bringing the contactor back from the critical. So you need to go a substantial amount of distance before it goes back to this flat film configuration, and this is done by pulling the contactor and elongating these columns to a certain region, so this energy barrier can be given by that. And what to be noticed is that this is a energy diagram for a single Fourier mode. They are impractical. There are several such Fourier coefficient modes, so this landscape is not as smooth as you are seeing. So there can be a lot of minimas over here. So your film can hop from one minima to the other before it goes to the flat film configuration. How it does, it depends on how you are pulling the contactor out, right? Whether you are using some noise in it, right, or what is the speed of the retracement, right? It depends on that. So if you do the nonlinear analysis, that is what is happening here. The red arrow marks how the contactor is being pushed down. So here you can see that when we had pushed down, there was a wavelength, and these were the cavities that were forming, right, which forms a dispersed phase. And now you're pulling the contactor up. So this is the surface of the film that we are seeing. So there's a virtual contactor on top of this that is pulling the elastic surface up, and you can see now that these cavities have all connected, and this is giving rise to a columnar like structure, and after some time the columns snap back and give you the flat film configuration. So if this was a decritical where the instabilities had started, you can see that these cavities are joining, right? So there is a total landscape change, right, of these patterns that are forming, right? And then you can bring it and you can actually freeze these patterns at any stage to get the patterns that are forming, right? And then you can see the total range of patterns that you can create out of this elastic films if you can freeze these patterns. And of course the snap of distance is much higher than the critical distance at which it initiates. So, like liquid films, we are also interested to find out the miniaturized patterns in elastic films, right? And how to get this. So, what we can do is we can use pattern substrate in these cases. Right? We thought of creating pattern substrate and see that whether we can get miniaturized patterns in elastic films as well, because you can see that lambda is dependent on 3h, where h is the thickness of the film. So the question that comes is, what h will it take if you have a pattern substrate? Whether it will take a h minimum, whether it takes a h maximum, or an average h for that factor, right? Whether the wavelength will actually decrease if I have a pattern substrate. So we did the similar energetics, right, in case of this, but in this case you can see that the energetics is changing along the x direction, because the thickness over here is different from here, so the restoring forces are different. So we have done in this particular case we have done a linear wise elastic energy consideration in this case, right? And we have done the linear stability analysis in a similar way, and we can see that if the pattern amplitude is actually increasing, we can get a shorter wavelength, right? That is possible. But in doing so, we can also see that the energy concentration, so the interaction energy required is very high. That means that you have to bring the contactor at very low distances to have this instability is possible. So what happens actually in this type of pattern substrate, we can see in constellation, if I see these springs in this substrates to be of springs of different nature. So these films at different lateral lengths can be considered as to be springs of different interaction stiffnesses, and you can see over here this springs of different interaction stiffnesses can be considered in parallel, and then the K effective that we considered, we can take a weighted average of this different individual Ks, right? So W is the weightage that is coming from K1, where the thickness is very small, or H into 1 minus beta, and K2 is and 1 minus omega is the weightage coming from the film where the thickness is actually very high. And you can see from here, from this contours, it can be found that for beta is equal to 0.1, where the amplitude is very small, the weightage is close to 0.5. That is, both the springs behave similarly. So that happens when the wavelength is when the amplitude is very small, and both the films right on top of this pattern substrate and at the trough of this pattern substrate have similar behavior, right? So the weightage will be similar. But when beta is 0.5, when beta is actually increasing, you can see that W is increasing also. That means the weightage coming from the thicknesses of the films that are very small is very high. That means that this film, which has a lateral variation of stiffnesses, it actually corresponds to a film with a effective thickness that is only corresponding to H minimum, or the thickness or the lower thickness. So in these cases, from this linear stability analysis, we can understand that the wavelength will actually decrease in these films. So to actually understand this, we needed to do a nonlinear analysis, and we wanted to do over different substrate. And the way that we did previously was not possible, because the energetics would require solving as the coefficients, and the boundary conditions was very non-linear, so we could not get an energetics out of this. So for that, what we have solved is that we have used a finite element analysis. This has been done in a commercial software, Abacus, and we are solving similar expression that we are doing in case of the liquid films. Only in this case, the viscosity has been transferred with the shear modulus in this case, and we are not solving for the velocities but the displacement fields. And here we have not taken the total potential between two slabs, but each of this point we have taken a body force with respect to the contactor, right? And we have done the only one integration to get between the point on the film and that on the contactor. And this body force has been done in a way by through a subroutine in VD load, where this body force has been incorporated, and we have taken elements depending on the nature of 2D or 3D simulations that we had done. So this was done in finite element analysis, and what we have done, we have seen is that when when the beta increases, so this was done previously for sinusoidal and step substrate, and you can see that as the beta was increasing, the wavelength at which these instabilities initiate was found to be decreasing. So basically, this is exactly what the linear stability analysis had seen. And also one can see that the displacement was coming very low for higher beta. This also proved the point that the contactor has to be brought very close for the instabilities to start in. So why there was a change in wavelength, to be precise, one can do is that one can find out the displacement in these films, and one can see that while for smaller betas, the beta is equal to 0.1 or beta is equal to 0.3, the instabilities can start anywhere, right? So anywhere within the film, whether it is on the crest of these patterns or on the trough of the patterns, it didn't matter that much, right? It can be anywhere that one can see. Whereas when the patterns amplitudes were very high, it can be seen that the wavelengths were initiating at the regions where the thicknesses were very high, or where the film was very compressible. So the wavelength of the pattern was in some way dictating the wavelength on the top surface, and for the same amplitude of beta 0.7 over a sawtooth profile and over a step profile, you can see that the wavelength can change. So it depends not only on the amplitude of the pattern, but also on the nature of the patterns. So what we had seen in the 2D simulations in finite elements also was that as the surface length scale of the substrate roughness increased, we were able to get wavelengths that were smaller in size, and this wavelength was dependent not only on the beta, so it decreased as we increase the roughness of the substrate, but also it depends on the nature of the substrate. So we had step, sine, saw, and random sine profiles, and you can see from this expression that for step profile the roughness is the highest, and for the sawtooth profile the roughness is actually beta by root 3, which is the lowest. So one can see that where it was a roughest profile, the wavelength was less, whereas for for less rough profiles the wavelengths were found to be higher. So once we recast this wavelengths over RMS roughness rather than the amplitude, one could see that we could cast these wavelengths over this RMS roughness, and it was linearly decreasing with the RMS roughness. So it fall on a master curve if we did this scaling with respect to RMS rather than the amplitude of the roughness. So we had done the simulations for different types of profiles, and we have seen that if the roughness was nearly same, the wavelengths would be also same. So this actually gave us a very important lesson that it did not depend on the type of substrate that you are looking, because this substrate creation would also cost a lot, because you are trying to create geometrical patterns. We'll come to this when we come to the experiments. But if we do it on on any surface, right, which with a different RMS, with the same RMS, the wavelength is going to be also same, and it is going to decrease. That was the main objective, right? That if we get miniaturized length scales, then we would get better properties at the surface. Moreover, if we can see the stress profile over here, so when the beta increases, we can see that more number of stresses are formed, though the magnitude of the stresses remain the same, but because of the stress concentrations, the force required, pull-off force required, maximum pull-off force required also increase. So this increase the work of adhesion of this type of films. So for any adhesives, one would understand that the increase in work of adhesion is a foremost thing that one looks into an adhesive film. So it has also been seen that if the velocity of withdrawal is less in these cases, the work of adhesion should also increase. So that is what has been found in this case of pattern substrate films. So depending on this analysis, we had done some experiments also, and we have taken rough surfaces, that of CD surface, EBM created surface, and that of water lily leaf that is naturally available also. And what we have done is we have taken this templates, we have cast this PDMS, thermally cured it, make it rough, make it very tough, right, so that an inverse replica of these surfaces could be created, as you can see over here through this AFM or optical images. And what we have done is we have seen the wavelengths across this over these films, right, that was cast on these substrates, and it was seen that indeed that the wavelength, as has been predicted by the simulations, that the wavelength was a function of RMS only, and it did not depend on whether we created a costly surface like EBM or whether we took a natural leaf, right, to create the rough surface. So we could create length scales that was very less. As we have told previously also, that you can take a different potential. Is not only you do have to depend on van der Waals interactions. So here you can create an external potential by creating an electric field through a voltmeter, and we have seen that in these cases also we could get patterns at the length scale of thickness of the film. So these are experimental results where you can get beautiful patterns. So that was one thing that we did with a different potential. In case of elastic films, it can be seen that you can get patterns like columns, labyrinthic structures, or cavities. And in all this case, because it it's an elastic film, one has seen that the wavelength actually varied as 3h. So the wavelength of the patterns didn't change, but the nature or the topography could change either by changing the h by d ratio, where h is the thickness of the film and d is the gap distance. So one can see that if this ratio is very small, or the gap distance is very high, one can get columns. Whereas if it is very low, so that the distance is very high, so that the distance is very low, then one can get cavities. And in between these two structures there are the stripe patterns, and you can have this by changing the voltages as well, right? So you can go both ways to create these different patterns, which are very much ordered, which can be used specifically for creating these commercial structures. Now you can change the strength of the field by taking a contactor which has a protrusion like this, and you can create the patterns at whatever distances you want, but then the wavelength will always remain the same. That has to be seen. And this was an accidental pattern that was created because of a dirt present on the contactor, and you could see that there was a satellite there was a hole and a satellite hole formation because of this in this type of film. So with the help of E-field, the concept of controllable and tunable addition comes in, because you can control the strength of the film. With Van der Waals interaction, you can never control the strength of the film, right? It always remain the same, but you can bring in at, and also you can see that the electric fields are rather long range than Van der Waals interaction. So the columns that you can form are much higher than those found in a case of Van der Waals interaction. So it can be totally controllable, right? But you cannot control on the wavelength. That is actually found out from the energetics of the film. But you can control like the voltage or the thickness or the amplitude or the aspect ratio of these patterns that are created. So now the question came was that we could get very good orders, right, with electric field, but then if we have a pattern substrate and an electric field, so the pattern substrate we could understand that the stiffness of the film changed laterally, and with an electric field, with the pattern contactor you could understand that you can change the electric field intensities over lateral direction. So if both of them are made to change in laterally, then what will be the instability like whether it will give a ordered pattern, whether it will give an pattern at a smaller wavelength, that was seen. The other energetics, the elastic energy does not will remain the same, whereas the interaction potential will change laterally. So if we see this, it can be seen that for yes, depending on h by d ratio, again one can go from columns, trimes to cavities, and at smaller patterns, while the patterns are have a very well ordered. First of all, it is not formed throughout the film. It has been formed in regions where the interaction energy is higher. Like at the top of this crest, right, where the film is there, and the interaction potential is very higher. So the instability is initiated over here. Moreover, it loses its order structure that we have seen for smooth substrate films, right? So this was not of much help to us, right? So what we wanted to do is that we wanted to ramp up the voltage and see what is happening. So one can see that if one ramps up the voltage, so the patterns actually that initiated at the edges could reach the regions where it was not present before. So it was moving radially inwards because the voltage was being pushed up, and in these cases one can see that all the three properties that we have seen of cavities, labyrinths, and columns that are forming to be present in a single film. So this is very important, because as we have said in case of peacock's feather, right, because we have these arrays of different sizes, different shapes, right? So this type of different structure colors were coming. So these properties can happen over here because of different types of patterns that were created. This was never being able to be formed over a single smooth film. Similarly, if we started with a voltage that was greater than this voltage that was present at an average thickness, it could be seen that one can get different types of structures, like this totally linear structures that can be used in microfluidics. So it can be seen that in the top row and the bottom row, the two last figures are of mostly at similar voltages, but different types of patterns on the same type of films has been formed, right? So it all depends on the initial voltage, that where the initial structure is struck and how you are making this propagate by increasing the voltage. So one of the question that comes is that with this E field, as we have seen in case of smooth surfaces, whether we can get patterns that are very small wavelengths throughout the film or not, because in many applications that may be one of the necessity, like in smart adhesives and things like that. So that also one can do, right? If the elastic film and the top surface can be uh, uh, can be can be cast in such a way that the interaction potential, or the interaction variation along the lateral length actually can be negated, and only the effect of the elasticity because of the different change in the pattern substrate can be kept in. So this can be done if the contactor can be patterned in a similar way as the substrate, so that the effect of the contactor and the elastic surface, that the interaction potential that has been changing throughout the lateral length can be totally negated. So if it is totally negated, one can see that yes, it can form these patterns of uniform length throughout these thicknesses, even as beta increases and the wavelength actually decreases in certain cases. And from by ramping in the voltage also, one can get these different patterns of columns, cavities, and labyrinths by simply changing the voltage of the pattern. So we have talked about these liquid films and elastic films today, right? Depending on the nature of the rheology and how we have solved it, we have seen that we have used a finite difference method in the first case, and energetics, or the finite element method in the other case. These two type of branches of fluid instabilities has been initiated into different directions, considering that they are totally different genres of film. So there is a lot of mystery depending on that, whether a film is an viscous film or an elastic film. Different types of behaviors has been seen. So the main question that came after solving all this was that, can we develop a mathematical model that can unify the observations that we are seeing in both these types of films, or basically can we cast a mathematical model for a film which is actually viscoelastic, which shows both viscous and elastic behavior. So for that case, we will try to develop a model for a common unified film, one that is in adhesive contact. So this film will be considered only as adhesive or free film. We won't try to differentiate it depending on the rheology of the film. So it's an adhesive film when it is in contact with a contactor, or it is a free film when it is when it has a free surface, right, and it is not in contact with another confinement. So we can do a force balance. We take a shaded area in both these films. We do a force balance. It will be the same in both these films, with the assumption that that there is incompressibility condition in the film. There is negligible inertial effects in the film. So the stresses that we consider, the constitutive equation that we take is that of a linear model of viscoelasticity. So where mu is the shear modulus and eta is the viscosity of the film, u is the displacement, and u dot can be considered to be the velocity. So this is for a viscoelastic film. If I consider, so the Nevius equation of the viscoelastic films can be converted into the following two equations. And the boundary conditions remain almost the same. Is a rigid substrate, no slip and impermeability condition at the substrate, shear free surface, because we are considering that is no shear. The bounding liquid is that of a gas or a fluid that has a very low viscosity, and there is a normal traction at the surface. which is compensated because of the surface tension effect. And there is of course, the excess intermolecular interactions at the surface. So this interaction energy for van der Waals interactions, this will be given by minus a by 12 by xi square. Please understand this xi. This xi is different for the two cases that we are considering. For adhesive behavior, this xi is the gap distance between the film and the contactor, and this xi is the local thickness of the film in case of the free film, and this delta G has been expanded through a Taylor series expansion, where Y here is the interaction stiffness of the film that we were considering. So if we take this and if we try to equate this depending on the Taylor series expansion ideologies, one can find out that these are the different values of the coefficient delta G0, F and Y for the two cases. The only thing that is different you will see is over the second term F over here, because it is dependent on xi, and xi, how it depends on V, is different in these two cases. So you will see that the interaction force phi again can be found from this delta G by taking a derivative with respect to F, with respect to V, and this exactly comes like this. So for a homogeneous film, what happens is that the displacement actually vanishes and the pressure is actually given by minus F. So it is different for both the cases, right? In adhesive films, while the pressure is considered to be positive, so means it's a tensile pressure, where in case of free film, it can be considered because of the negative sign over here, that is a compressive pressure that is arising because the substrate is trying to pull it, and in case of adhesive film, what is happening is that the contactor is trying to pull it. So the entire film can be actually both the configurations, any rheology can be considered by considering this viscoelastic film. And let us see, by taking an inhomogeneous solution to this film, what do we get? So if I take an inhomogeneous solution like the trial function like before, right, in this case the only difference is that we are not only taking this displacement as a function of x and y, but we are taking a time component of it, because we are considering that this displacements are varying with time as well. Not for in elastic films we didn't do it, in viscous films previously we did it. So here we are taking it, right, and we take a dispersion relationship out of this, and in this dispersion relationship we can see that there are certain non-dimensional quantities that are coming into play. One is the growth rate, which is eta omega by mu. So all these are non-dimensional numbers which we can understand to be the ratios of equivalent quantities. Gamma by mu h is the ratio of surface energy to elastic energy, minus yh by mu is the surface ratio between the interaction energy to elastic energy, and hk is the weight number of instability. So we can see that there is an interplay of all these energies, all these non-dimensional numbers, that actually give rise to different types of behavior in these terms of adhesive and free films. So different limits, if I want to take the elastic limit, one can take by considering that the viscosity in the film is negligible. Once one takes that and can further do it for thicker films where H is very high, one can take that this is the interaction, this is the energy that we get, energetics that we get. This is exactly the equation that we are solving for shortwave elastic equation. Similarly, if we take the viscous limit, where we have taken a long wave approximation, where we have taken that the wave numbers are approaching zero, then we will get this dispersion relationship, where we can take, if the viscosity, if the shear modulus or the elasticity is zero, this is exactly the dispersion relation that we had got for viscous films. So basically, we can get the asymptotic cases if we take different regimes. But if we are talking about a viscoelastic film, one can see that there is a critical wave. So there is a critical stiffness beyond which there is instability in the system. So if you see the cross section in film B, so above this critical interaction stiffness, there is a region, right, where instability is possible, and these are bounded by the neutral wave numbers, and there is a dominant wavelength where the instabilities actually grow, right, like in liquid films that we have seen. But in liquid films there was no critical interaction mode that was present, right? All instabilities under a certain thickness was unstable. So one can see also the effect of elasticity. So as we go from the red curve to the blue curve, if we see over these equations, if the surface tension and the thickness of these films are kept same, so we are actually increasing the elasticity of the film. So if mu increases in this region, one can see that the instability region is actually decreasing. Similarly, if the surface tension increases in this films in figure B, one can see that the instability region, or the region above eta omega by mu, or where the growth rate is actually greater than 0, that unstable region is actually decreasing, and one can see that the dominant wavelength is also moving towards lesser values. Wave number is moving towards lesser values, means that it is becoming more longer waved as surface tension effect is increasing. So one can see that actually in elastic films, the restoring, so if you are making a film unstable, the restoring force is actually the elasticity of the film. And in case of liquid films, if you are making the surface unstable, the restoring force is again the surface tension. So the increase of both these quantities, what it is doing is it is making the film stable. So this is the effect that one can see, that if one is increasing this effect, how the instability zone is decreasing. Similarly, if we see the critical conditions of instability, so the critical interaction stiffness, one can see that if the surface tension effects are increasing, so the energy penalty required as given by the blue curve is seen to be increasing. This means that you have, in case of the elastic film, it means that the contactor has to be brought down to a much lower value to have this instability is possible. Similarly, to understand the effect of basically the shear modulus, one can see that if the mu value is very less, that is in case of where we are going to viscous film, if we are going to the right hand side of the X domain, this is a region where we are getting into the viscous film, one can see that the critical interaction required to bring in instability is actually decreasing. That should be the case. It will actually go to 0 in case of films which does not have an elastic effect present at all. So any film that is in case of viscous films should be unstable. There should not be a critical condition for it to be unstable. There was no thickness, right, below which it should be unstable. So if the interaction stiffness is felt, then it can become unstable at any thicknesses. So there's no critical interaction stiffness. So one can find out the wavelength. Again, it can be seen that it is only dependent on the parameter gamma by mu 8, the critical interaction, critical wavelength that first initiates. It can be seen that where the surface tension effects are very important, that happens in cases where, of course, the surface energy is very high, or the shear modulus is very less, or the thickness is very less. So in that case, one can get long wave regime. Whereas in case of where the surface tension is low, or the thickness is higher, or the shear modulus is very high, shear modulus is very high, especially in the elastic cases. So one can go to this gamma by mu h values to very low values, and one can see that this short wave instabilities actually persist over here. So one can get in a single understanding that where one can get the elastic like behavior, and where one will get the viscous like behavior, right, and where the transition will take place, and that all depends on the value of this surface tension gamma by mu h to be definite. So basically one can see also that that when you the inset of this figure is for the surface tension values to be very less, and in case of wetting films this can be seen to be happening only for sub nanometer length scales, which is not a possibility. So this actually tells that if the surface tension effects are very less, and if you want that to happen, that cannot happen for a wetting film in elastic films also. So even in elastic films, if you cast it in a wetting film configuration, it will give you a long wave wavelength. And basically, if you put in certain surface tension as low as 100 Pascal also, as 10 to the power minus 2 Pascal also, this restricts a critical thickness below which the instabilities will be possible. So normally, if the shear modulus is actually the shear modulus is very less, this HC we should go to infinity, right? So it can be any film that will be actually unstable. But in this case, there is a criticality that has been brought in because of this shear bringing in of the shear modulus. So all these critical conditions has been found out to be dependent very much on the elasticity of the film. It is not dependent at all on the viscosity of the film, to be very precise. And one can see that the wavelength, the dominant wavelength, on the other hand, is only a function of this parameter minus h square y by gamma, which is obtained by the ratio of the interaction stiffness to the surface tension stiffness. And this HKM is a constant for very high values of this quantity, and for very less values we see that we are going to the long wave approximation, or that is found in viscous films. So we can see that in case of elastic films, when the surface tension fx is very high, then the wavelength that was formed to be 2.96h, that also goes to a long wave regime, right, when the surface tension effects are very high. So if we don't care of the thicknesses that we are doing, if the thicknesses are very less, in order to get this instabilities at very small length scales, it won't help us, because in that case surface tension effect will come in and will actually make the wavelengths longer waved in that scenario, right? So the surface tension effects comes into play if the thicknesses of the films are very less. Similarly, if you cast a elastic film in a wetting configuration, it can be seen that it actually gives rise to long wave length, right, according to long wave length. And it can be seen as a very interesting phenomena that when the thickness is very less, you can get islands, right, of these instabilities, whereas when the thicknesses are high, you are getting things like cavities over here, right, that actually develops in wetting liquid films. So basically what it tells that the rheology gets marred, right? It is only the geometrical configuration that dictates what type of instabilities will be done. So even in elastic films, so is certain parameters that we have to look into. So if it is if the surface tension is very high, then we will definitely have long wavelengths, right? Surface tension effects will come into play, and even in elastic films we will get wavelengths that are long wave. Whereas if we cast in a wetting film, then it is not possible to get short wave even in elastic films. It will again get long wave, right, because of the morphology or the configuration of the film. So I think today we can stop over here, right, because wet granulus is going to be a totally different manner, right? Yes, Anurag, is that okay?
Yes, ma'am.
Yes.
Thank you, ma'am. Thank you. Very interesting and very energetic lecture. So now it's time to question answer. So, dear participant, you have any question, you can ask to directly.
Well, Dr. Anurag, this is
Yes.
Arijit. So,
Yeah.
Professor Sarkar,
Yes,
this
I
is
can hear.
Arijit. Yeah. So, I first of all acknowledge that it was so comprehensive. I am a very new person to this topic, and it was really, you covered everything like liquid films, elastic films, viscoelastic. So, uh, my I have a lot of questions, but I will ask a very simple doubt right
Okay.
now, because this is not a forum that I can ask a lot of questions.
Hmm.
Uh, in the first part, where you showed before the linear stability,
Hmm.
uh, 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 if I have not mistaken, it was solved only using analytical solution, right? Only with the boundary conditions.
Yes, 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 yes.
Okay.
So,
Uh, so, so generally, as per the experience, what we have with analytical, we make a lot of assumptions,
hmm.
and then we arrive at a certain expression where we have a certain
Hmm.
solution, probably distribution or anything. So, how reliable it is to go with the United solution, and how do we solve, say, partial differential equation of fourth order? Um, can we solve it by normal numerical techniques, or we have to go like you said for non-linear stability? We have the finite difference or here algorithm and all.
Yes,
Uh,
yes. Let me answer one by one. Very good questions. Basically, yes, long wave approximation. The word tells approximation, right?
yes,
So there are a lot of approximations over there that we are taking. Like we are taking that the stresses at the boundaries are zero, right? Just starting from
right.
the boundary conditions, right? We are taking
Yes, yes,
a
yes.
lot of
Absolutely.
yes, so there will be a drag if there is a viscosity present. If there,
Hmm.
we are totally neglecting it, right? So
Yes,
if there is a vapor, even it can be an evaporating film, right? Because we are constraining films at a very high temperature. There, I mean, so there are a
lots of things. Yes,
lots
yes.
of assumptions that we are taking. So this lubrication approximation, what we do is we try to modify the Navier-Stokes equation so that we can get an equation that we can is a simplification, right?
Right,
Is
right.
much simplification than solving the actual Navier-Stokes equation for this type of thin films. So is
Yeah,
an approximation, very much an approximation. So, but the test of the pudding is in testing, right? Is in
yeah.
happening. So
Absolutely.
basically, what happens is experimentally you can see that actually the wavelength is varying like thickness is square, right? So certain
Okay,
things are matching. But
okay.
if then you do the experiments for those parameters for which you are doing the simulations for, right? But there are
Yes.
certain different conditions where we don't get the linear stability analysis results or even the non-linear stability analysis results.
Okay.
So I mean, yes. So
What do we do for such type of situation? Like how much will might be the deviation, and then how do we counter these things? Because this is a very very complicated
yes, I mean
equation that we
even
are solving.
yes, even
So,
if you solve it, you get a partial differential equation of fourth order,
fourth
which is
order, right, right, which is very difficult. I know.
yes, easy to solve. So solving this in entirety is really difficult. So what actually in our group we are trying to do because of these things is that we are trying to now use LBM modeling, lattice
Okay,
Boltzmann
that is
modeling.
Boltzmann modeling. Very good,
Yes,
very nice.
yes. So I wanted to actually show I mean something on weight granulars, but today it didn't.
No, that's
Yeah.
fine. I think you have covered a lot. So
Yes.
thank you.
So yeah. So
Thank
this lattice Boltzmann modeling and other things would preferentially be able to help us in getting rid of some of the assumptions that we are taking and getting us more closer to the actual real situation.
Okay, okay, okay.
That is.
Thank you. I think that answers my question. Thanks a
Okay.
lot. Proceed.
Thank you.
Yeah.
Anyone?
Yes, ma'am.
Yes.
Good afternoon, ma'am. I'm a PhD student, and I have my few basic questions. So, first
Hmm.
of all, I would like to ask you that could you please throw some light on short wave and long wave approximation? I mean, how could we arrive to that before approaching our problem? I mean, before having a derivation of that.
Okay. So basically, these are guided by the experiments. All these solutions that we try to do, like the experiments showed us, right, that that the wavelength is actually. So it depends on how the wavelength is related compared to our thickness of the film. So if it is like h square means as the thickness is increasing, the wavelength is increasing square of it, right? So if I instead of taking a 1 nanometer film, if I take a 2 nanometer film, if my wavelength was 1 nanometer for the first case, it will be 4 nanometer for the next second case, right? So it is varying. So as you go on, it may be very difficult to do a very small thickness, right? So if you are substantially increasing your thickness, then your wavelength is going to become higher and higher, right? That is what is a long wave approximation is. If the power of h that you are varying your wavelength with is positive, and is it if it is higher than 1 or something, then your wavelength is long waved, right? And this is totally found experimentally. right? Before going into this simulations, people tried to see the experiments how it was forming, and in case of elastic films, it was found that if it changed linearly totally. So that's why we are talking that it is short wave, because it depends on the thickness. So if you're increasing from 1 to 2, your wavelength is only becoming approximate to 6, right? Because it is 3H. So things like that. So it varied linearly, and on the other way, the other varied in a power law way, right? As h square. So that's why we are calling wave short waved and long waved, right? So if it is varying close to h, then you cannot take those long wave approximations. So that's why you may see that in the elastic films we have not done by the long wave approximation. We have not used that approximation, because we have constant, we knew from the from the experiments that it was short wave, right? So because ultimately it's a force balance, right? We could have gone to the same way of solving, but we have not done it, because in that case it's a short wave short waves that we are getting. Similarly, for miniaturization of patterns, no one asked me, but if the viscosity variation is giving me smaller length scales, we may reach a limit, right, where this long wave we can solve by this long wave approximation, because it can happen that the wavelength is not following h square but some h to the power something else, right, which is lesser than 2. In that case my whole theory will fail, right? We cannot use that long wave approximation anymore, right? So that's why we are rapidly developing this lattice Boltzmann method, so that to deal on liquid films that have that can be dealt if things are short-waved in that case. So it depends on how it is related to the thickness of the film.
So, ma'am, you mean to say before declaring whether it is short wave or long wave, we have to have some experimental backup, like, am I right? I mean,
Yes,
so that.
yes. So the way these things actually developed was to understand the physics behind this, right? And this goes hand in hand, right? You need to know both the experimental results and theoretically predict those results, right? And then do newer things, and then find out experimentally whether your predictions that you are doing is correct or not. That's how this.
But
Huh.
yeah, I mean, all the theoretical people generally say that, like, I mean, that is the beauty of simulation, that beforehand, I mean, before approaching any experimental setup or something, like, we have beforehand results, I mean, by doing simulations, and then we can approach the very optimized experiments with the help of that simulation. So in this case, that is not the case, you mean to say, am I right?
Sure, sure. See, I am a theoretician throughout my life. I've done theory only, right? So, theory, but in some way has to match with your experimental result. Some way you have to apply it somewhere, right? So, and to see that whether it is matching or not, right? So, we do a lot of predictions, right? And that's what the beauty of simulation is, right? If you can do do the prediction, but then the prediction can differ depending on the assumptions that you are taking, right? So you can have different predictions considering that your wavelength, but that then the experiments come in to help, right? Some experiments, as we have said, optimize number of experiments. So yes, some experiments will give you a pathway to understand whether whatever assumptions you are taking is making sense or not. है
Yeah.
ना? So you have to do experiments. You cannot totally be blind and tell नहीं simulation ही करना है, right? You have to take care of both of these things.
Yeah. And ma'am, one more. Uh, I mean, kinematic boundary condition. Is it really a boundary condition, or just to track the interface in terms of the space and time coordinate? Because I mean, while solving these linear stability problems, I mean, I have came across recently few problems. So in that case, I mean, I had a biharmonic equation. In that, after having that, I mean, like assumptions like semi-infinite case. So there I have eliminated two constants. So I had two equations with four constants A, B, C, D. So in that case, I was considering the boundary conditions as at the interface normal tangential stress balances and continuity of velocity. So obviously U and W, those are the two boundary conditions because of continuity of velocity and because of those normal and tangential stress balance. So in that case, how kinematic boundary condition I have to take into picture, because I mean that is the confusion, that whether it is really a boundary condition or just to support other variables or some parameters.
Yes. So basically, in this case, it is to just to track the surface, right? How the velocities and the surface are related. You take care of the kinematic condition. Is actually not a boundary condition, but we are constraint. We are telling it boundary condition in this case because it consists of the thickness of the film. It
Yes,
is
right.
at the boundary. It's not a boundary condition. Kinematic condition can be at any place on Z axis, right? If you consider, right? Um, yes.
Okay, so that means while forming that coefficient matrix,
Hmm.
while forming that coefficient matrix, then I need not to consider that edge as a variable. I mean, as a constant. Then that came into picture because of this kinematic boundary condition.
Yes, because you are considering this, right? Because you are solving the for the thickness, right? That's why you have considered this condition.
Yeah.
Otherwise, if it is not required, people don't use this condition, right?
Okay.
It depends on how many boundary conditions you require to solve the problem.
Okay. Mm-hmm.